All right, today in Chem 100, we're going to start a review of all the material we've covered in this course from the very beginning to prepare for final exam. Let's see, the final exam will be, this is Tuesday, next Tuesday, which will be May 7th. We have 2 days to do this review. So I've selected ones that I want to be sure and cover. And if we don't get it all done today, then we'll pick it up again on Thursday. But if we do finish today, then I'll follow my pattern and I will zoom in on Thursday for about 30 minutes in case someone zooms in and wants to discuss their problems. Otherwise, we're going to get rolling with number one. Now, this review document is in Brightspace. And there's also a key that should look exactly like this one without the yellow in it. And there's also a worked problems. In other words, for those, if you are working through this document and you can't figure out where you're going wrong, look to the work document and it'll show you how at least one way that I solved a problem. And hopefully that'll give you an insight. Otherwise, we're going to go through and work these yellow ones one at a time. All right. Water has a density of 1 gram per milliliter. All right. So the density of water equals 1 gram per milliliter. Right. Which of these objects will float in water? Right. The one principle that you need to recognize in order to solve this problem is that if the density of the object, let's say object 1, 2, or 3, if the density of object is less than 1, it'll float. If it's greater than 1, it'll sink. All right. So what we have to do is determine the density of each one of these objects and compare it to water. All right. So we've got these 3 objects. And in order to, since our comparison density is water at 1 gram per milliliter, we really don't have to calculate exact values for each one of these. You can if you want. But all we have to do is decide, is the density of this one equal to, less than, or greater than 1? So if we look at the mass at 50 grams, I can do better than that. 50 grams per 69.4 milliliters. Right? Is that equal to 1? No. Is it greater than 1? No. The numerator is smaller than the denominator. So this quotient is less than 1. That means the density of 1 is less than 1, and it will float. All right. The next one is 16.9 grams, 60.9 grams per how many milliliters? 54.7 milliliters. The denominator is smaller than the numerator. That means the quotient is greater than 1. Greater than 1. So the density of 2 is greater than 1. This one will sink. How about the last one? 100 grams and 40 milliliters. All right. That is greater than 1. So the density here is greater than 1, and it will sink. So the question was, which of the objects will float? Only one. That one. And in your selections, that is B. All right. Let's look at number 2. Which of the following describes a chemical property of gold? Remember the difference between chemical properties and physical properties. Properties are, when you think property, think potential. What is the potential for the object being described? Is it a potential of, well, let's look at it from a chemical standpoint. If it's chemical, it has the potential to change identity. Right? So a physical property would describe a change that doesn't change the identity of the object. Okay, so if we're looking for a chemical property, we want a description of the potential that could lead to a change in identity. All right, gold is a very dense metal. Density refers to a physical property. There's no change in identity. Gold is a soft metal, right? That's a qualitative description of gold that has nothing to do with its with any possible change in identity. Gold is an inert, non-reactive metal. That speaks to whether or not gold will change its identity in a chemical reaction. Right? It is inert. Its potential, its chemical potential is that it will not change its identity. But we're still talking about the identity of gold. That's why C is the best answer. Now, D and E are both referencing physical properties. Yellow, color, good conductor of heat and electricity, those are physical properties. Right, so C for this one is the best answer. Number 3. How many significant figures are in the number 1000.0, right? Yes. Remember your rules for significant figures. You have non-zero numbers. All non-zero numbers are significant. So that one is significant. Right? Then you have different types of zeros. Zeros to the left are not significant. We don't have it here. Zeros to the right are only significant if there is an explicit decimal point. There's your decimal. So we have 1, 2, 3, 4, 5. 5 significant figures in that number. All right, let's go ahead with 4. We're talking about using the same rules, 004, 009. 0. Okay, how many significant figures are in this number? Well, we've got that one significant and that one significant. These are not significant. There's a decimal there. So this one is significant. How about those 2 zeros? We didn't talk about those. If you find zeros between 2 non-zero numbers, they are significant. That's right. 1, 2, 3, 4, 5 significant figures in this one as well. Number 5. Number 5, which is an example of a homogeneous mixture? Remember, a mixture is a combination of two or more substances that retain their identity in the mixture. All right. For instance, you can mix sand and salt together, and they still retain their identity in the mixture. Additionally, these mixtures can be separated, the components can be separated by physical means. You don't have to do anything to the identities to separate them. You just need the proper approach to separate the mixture. All right, so a homogeneous mixture is one in which the composition is uniform. The composition is uniform throughout. What does that mean? That means anywhere you sample that mixture, the ratio of components is exactly the same every time. Everywhere you sample, the percentage composition of each component is the same. That's homogeneous, uniform throughout, as opposed to heterogeneous, where different sampling positions will give you different compositions. All right, so which one of these is homogeneous? I mentioned during the previous lecture that soil, and here they're saying dust, but soil of any kind is heterogeneous. It does not have a uniform distribution of particle sizes or materials of any kind. Sodium chloride is not a mixture. Sodium chloride is a compound. Right? All right. So it doesn't even qualify as a mixture. Aluminum is an element. It's not a mixture either. Vodka is an alcoholic beverage that is primarily water and ethanol and maybe some other components, but they are all uniformly distributed throughout the mixture. Vodka is a homogeneous mixture. There's another word for that homogeneous mixture. We call it a solution. Now, oily water obviously is not a homogeneous mixture because you mix oil and water together and they don't stay mixed. They separate. All right, so we got D for that, number 5. How about number 6? A cat is 7.1 pounds. Right? 7.1 pounds. That's the mass. Right? What's the mass of the cat in kilograms? Right? And there's your conversion factor. Remember, every conversion factor is derived from an equality. So when we say 1 kilogram equals 2.2046 pounds, we can create a conversion factor. Remember how we do that? Well, we need to convert pounds to kilograms. That means pounds has to be in the denominator to cancel, and kilograms in the numerator. So we want kilograms in the numerator. That means we need to divide both sides by 2.2046. 2.2046 pounds. We did the same thing to both sides, which is permitted in math. This is equal to 1. And this is what is equal to 1. Remember, all conversion factors are equal to 1. That's why we can multiply this times that quotient, and we haven't changed the physical amount of the substance. We've only changed the units of measure. So if we substitute for 1 in here, 1 kilogram is 2.2046 pounds, then we end up with kilograms, right? And if we do that math, and remember, multiplication rules. This one has 2 significant figures. That's an exact number. It doesn't count toward significant figures in your answer. Your answer will have 2 significant figures because this abides by the multiplication and division rule. So we have 2 significant figures, which should be rounded to 3.2 kilograms. Now, does that make sense? Right? Does it make sense? This is a little more than 2. So if we divide 2 into 7, we get 3.5. If we divide a little more than 2, then we get a smaller than 3.5. 3.2 is in the neighborhood. So I'm satisfied that we've done the calculation correctly. Let me see. I'm going to refresh this surface. All right. Let's see. We're going to skip 7. That's another conversion. Which of these is a chemical property? Right? A chemical property is going to describe the potential for a change of identity. If we say that ice melts at 0 degrees, has there been a change? Is there the potential for change? No. You still got water. It would just possibly change phase. How about B? Water has a high specific heat. No, it's still water. We're just describing its potential to absorb heat or release heat. How about C? Sodium is a soft, shiny metal. That's a physical property. Right? We haven't even touched the ability of sodium to change its identity. D, helium is a very non-reactive. That speaks to chemical property. Reactivity is a chemical property. So helium is a very non-reactive. D is the best answer. And then, of course, glycerol is a viscous liquid. We're still talking about physical properties. So D is the best answer for that one. Let's do number 10. All right. 485.5 K. 485 K, which is what? It's an expression of temperature on the absolute Kelvin scale. Now we have options here: degrees Celsius, degrees Fahrenheit. So the first thing you have to do, if you have to go to Fahrenheit, you got to go to Celsius first. So let's go to Celsius first and see if one of those answers is there. Right? So what's the relationship? Well, Kelvin is equal to degrees C plus 273. All right? So if we want degrees C, that means K minus 273. So we subtract 273. Right? Let's see, 5. There's some decimals out that we could put decimals out there, but to find the right answer, we don't need them. So 3 from 5 is 2. 7 from 8 is 1, and 2 is 2. So 212.5 in that neighborhood. Is there anything close to that? Yeah, D. D would be the best answer. We didn't even have to convert to degrees Fahrenheit. We converted Kelvin to degrees C, and the answer's there. All right, let's scroll down to another one. How about 14? Okay, which of the following is only a physical change? Only a physical change. Now we're talking about the actual either change of identity or not change of identity. When a change occurs and the identity of the substance did not change, that's a physical change. On the other hand, if there's an explicit change and the identity of the substance does change, that's a chemical change. So which of the following is only a physical change? All right, A, leaves turn colors in the fall. All right, let's take these one at a time. When leaves turn colors in the fall, what are we witnessing? Well, we're witnessing a change in color, which normally would indicate only a physical change. But we know from biology that when leaves change colors, there is a chemical change going on in the leaf. In other words, the chlorophyll is being degraded, chemically degraded and recycled. And what's left behind are the other colored pigments in the leaf. The xanthophylls are the yellows, the anthocyanins are the reds, the carotenoids are the oranges. So those are left behind because the chlorophyll is degraded. So there's both physical change and chemical change there, right? This is not only a physical change. So A can't be it. It's both physical and chemical. How about B? A banana ripens. That's a chemical change, right? When a banana ripens, it is releasing a gas that's not there in the beginning. Well, it's releasing several gases, actually. Ethylene oxide is one of them, which accelerates the ripening as well. So that's a chemical change. How about C? Cookies burn in the oven. That's a chemical change. When you burn something, you are oxidizing it. You're adding oxygen to it and producing a reaction in which a product is produced that wasn't there before. Now that burning is a very, very complex reaction. So we're not going to talk about that. D, sugar dissolves in coffee. That is purely physical. Why? Because the sugar didn't change its identity. The water didn't change its identity. If you want to get the sugar back, all you have to do is remove the other components of the coffee. The sugar's still there. E says at least two of the above exhibit only physical change. No, that's wrong. Right, it's just this one. That's the one that has only physical change. 16. All right, if a 100-gram sample of a metal has a volume of 8.65 milliliters, what's the density of the metal? All right. By convention, usually solids are given volumes in cubic centimeters. But since 1 milliliter equals 1 cubic centimeter, the calculation we perform here will be equal in value for either units of measure. And since the answers are given in grams per milliliter, then we might as well stick with what we've got. 100 grams, right, density equals mass divided by volume equals 100 grams and 8.65 milliliters. Notice that both of them have three significant figures. 3 here because they're all non-zeros. 3 here because we have an explicit decimal. So our answer will have 3 significant figures in it. It should have. So we can estimate if this number were 10 divided into that, then our value would be close to 10. But it's smaller than that, so it should be greater than 10. So do we have any in here that are greater than 10? Let's see. 9, 1, 11.6 is greater than 10. That's the only one in there that's greater than 10. So you can use your calculator, right? And get that answer. But since it's multiple choice, we were able to estimate and find the answer. Oh, there's just one sticking point here. E says none of these. Right? So it probably would be better to calculate it and then compare the answers. Because if you get an answer that's, say, 11.5 or 11.4 or 11.7, then you could theoretically say none of these. But if we divide 8.65 into 100, we should get a rounded three significant figure answer of 11.6. The number 17. The number of 14.809. 14.809 rounded to three significant figures. Right? If we're going to keep three significant figures, which ones are the three? You start from the left and move to the right. Right? 1, 2, 3. So we want to round to that position. In order to do that, you look immediately to the right. Right? You don't look beyond the right. This one right here is less than 5. So that goes out, and our answer is 14.8. All right. Number 18. Which of the following is an incorrect description? Okay. Let's see. A, B, C, D, and E. How about A? Homogeneous mixture. Are those two terms compatible? Yes, because mixtures can either be homogeneous or heterogeneous. That's a correct description of a solution, a homogeneous mixture. That one's good. A solid element. Yeah, we're talking about phases here. Can elements be solid? Yeah, sure. In fact, most of the elements in the periodic table are solid at room temperature. C, a solution of gases. Is that possible? Yeah, I'm breathing one right now. A mixture of nitrogen and oxygen and some argon and some other trace gases. Yeah, a solution of gases is proper. How about D? A mixture of solids. Can we get a mixture of solids? Well, yeah. Salt and sand, for instance, is a mixture. Is heterogeneous. You can get a homogeneous mixture of two solids like an alloy, like brass, copper, and nickel would be a mixture of solids. Yep, that one works. So by process of elimination, I bet E is not a heterogeneous compound. Nope, can't be. Heterogeneous refers to a mixture. A compound is not a mixture. A compound is a pure substance. right? It's a pure substance. Compounds can be pure substances. Elements can be pure substances. They're not mixtures. All right, let's see, number 20. The state of matter for an object that has neither definite shape nor definite volume. Remember, solid, liquid, gas. All right? They can have shape and volume as defining characteristics. So a solid has a definite shape and a definite volume. A liquid has, and let's see, the terminology, say indefinite. Indefinite shape, but a definite volume. And a gas has both an indefinite shape and an indefinite volume. So I think we're talking about a gas here, right? That's the state of matter that is both indefinite volume and indefinite shape. 24. All right. 24. How many of the following are pure compounds? Pure compounds. To answer this question, let's work it backwards. Sodium, sugar, oxygen, air. Sodium, sugar, oxygen, air, and iron. Right? I use the symbols there because by now you've learned them all and you understand what that means. Okay? All right. How many of the following are pure compounds? Pure compounds. Let's work it backwards. How many are compounds? Right? That's not a compound. Air is not a compound that I know of. Oxygen is not a compound. Sugar is a compound. Sodium is not a compound. So the only one that's possibly pure in this whole group is, well, how many? Only one, right? Only one's a compound. Now, air could be a mixture, right? It's not pure. It could have a compound in it. It could have carbon dioxide, right? It could have some methane. Okay. If you go high enough in the atmosphere, it could have some ozone. Right? So it could have some, well, that's not a compound, that's an element. But it could have compounds in it. Could have some hydrocarbons, right? If you're close to a gas station, probably got a lot of octane floating around the air. But it's not pure because it has elements also. So the best answer is sugar. That is a pure compound. (26). Right. Let me see if I can make that a little bit bigger. Yeah, see that a little better. Which of the following is a chemical change? All right, we're talking about changing identity. Sugar dissolves in water. Sugar dissolving in water. Are we changing identities of anything in that arrangement? No. You still got sugar and you still got water. There have been no changes in identity. This is not not a chemical change. Gasoline evaporating. Do you still have gasoline after it evaporates? Yeah, it just changed phase. It went from a liquid to a gas. That's not a chemical change. Water boiling, right? You still have water afterwards. Now it's steam, but it's still water. No change in identity. It just changed its phase. Paper burning. You go from cellulose primarily in paper to carbon dioxide, water, and some ash, right? You have changed identities there. This one is definitely a chemical change. Melting butter is just a phase change, right? So D is our answer. That is a chemical change. All right. Let's see what 28 has to say. Scooch it over a little bit. Ooh, I guess I'm going to have to shrink it a tad. There we go. So I should have left it alone. 28. What's the most abundant element on Earth, including the crust, the oceans, and the atmosphere? The most abundant element, that could be interpreted two different ways. When we say abundant, what do we mean? The most number of atoms or the highest mass? Well, I think we're pretty safe to say that either way works. Because oxygen weighs, each oxygen weighs 16 grams per mole. And almost every element in the Earth's crust, in its oceans, and the atmospheres, well, oxygen in the atmosphere is 21%. Right? 21% oxygen in the atmosphere. But in the Earth's crust, well, in the oceans, right? You got all that water. It's mostly water, with about 0.35% salts of different kinds, right? So it's mostly water. There's your oxygen. There's your oxygen. How about in the crust? Most metals, very few exceptions, gold being one of them. Most metals in the Earth's crust are combined with oxygen, right? You got some metal and oxygen, and depending on the metal, you'll have a certain number of oxygens with it. So that tells us that the most abundant element in the Earth's crust, oceans, atmosphere is oxygen. You know, that might not be right. It could be, I think it's 3.5% salt in the oceans. And that varies, of course. The correct name for FeO. All right, now we're in nomenclature. How do you name that compound? Remember, there are three different types for naming conventions, three types of compounds. Okay. The first two are ionic, right? Metal, non-metal. So what do we have here? We got a metal and a non-metal. So this is either type 1 or 2. Now we have to break the tie. Which one? Is it type 1 or type 2? Remember, type 1, the metal has a fixed charge. It can be no other charge, just one charge, that's it. And which ones do that? Alkali metals, first column of the periodic table. Alkaline earths, second column, with a 2+ charge. First column is 1+ charge. And then there's aluminum, gallium, indium. They're all +3 charge. And then there's some in the transition metals. There are 3 of them in the transition metals. We've got let's see, silver, cadmium, and zinc. They are fixed charges. But iron is not one of those. Iron is a variable charge. Variable charge means type 2. Okay, so how do we name a type 2? Well, you start off with iron, and you end with oxide. Right? Just change the ending to IDE. And then you say, what is the charge on iron? Well, oxygen is a chalcogen. In ionic compounds, it's always -2. So that means iron has to be a +2. And we say, there's the charge on iron. Iron to oxide. And that would be B. Okay. How about 32? Let's see. Let me take a minute. Take a minute to refresh my board so it'll work better. There we go. All right, 32. When the following equation is balanced using the smallest possible integers, what's the number in front of the substance in bold? So what's the coefficient for iron? All right, let's see if this one will work with a budget method. Okay, so we're starting off with aluminum, and we have Fe3O4. Fe3O4 is going to yield aluminum oxide plus Fe. Okay, so our budget method says we have aluminum, we have iron, and we have oxygen. We have 1 aluminum, we have 3 irons, and 4 oxygens on this side. On the other side, we have 2 aluminum, we have 1 iron, and we have 3 oxygens. And remember, if you have any elements on either side, hold them till last. All right, so we have iron on that side, we have aluminum on this side. So we're going to have to focus on oxygens. How do you get 3 oxygens to reconcile with 4? The best way, since oxygen occurs in only one place here, one place there, the best way is cross multiply. So if we take that 3 and put it over here, and that 4 and put it over here, that gives us 12 oxygens on both sides. Now let's reconcile the irons. Now we have 9 irons, correct? And on this side, we have 8 aluminum. Okay? Now we can use our separate elements of aluminum and iron to balance the rest. We need 8 aluminum, right? And we need 9 irons. So the coefficient in front of the Fe is 9. All right? Okay. All right, scroll just a little bit. 33. A gas occupies 30.3 liters at 2 atmospheres pressure and 27 degrees C. How many moles of gas are present in the sample? This is working with gases, obviously. So now we have to decide, is this a before and after situation where you can use one of the gas laws? Or is this a state situation? In other words, we don't know how we got there. We just know these particular values of volume, pressure, and temperature. It's a state function. That means the only option we have is to use the ideal gas equation. All right. Now we have liters, we have atmospheres, and we convert temperature to Kelvin. Why? Because R. So we're going to solve for moles. Moles equals PV over RT. Right? You can look up R in useful information. It's in that separate document that'll be sitting there in the folder before you take the exam. You just print that thing out and keep it with you while you're in the exam. All right, this value is 0.08206 liter atmospheres per mole K. Temperature has to be 27 degrees Celsius plus 273. That will give you K. We have to do that because of that value right there. And whenever you're working with gases, you have to use an absolute system. So Kelvin is it. How about pressure? Pressure has to be in atmospheres. Do we have atmospheres? Yeah, 2 of them. Okay. How about volume? Volume has to be in liters. 30.3 liters, correct. I'm gonna go ahead and calculate this one just for fun. All right, so we got 2 times 30.3 divided by 0.08206. And 27 plus 273 is 300. Right, this is 300. Okay. And divide that into it. So I get 2.461613 moles of gas. Now, how many of those can we keep? Well, we've got 3 significant figures. This is a divide rule for significant figures. 3, 3, that doesn't count. That's a constant. And 3. Yeah. Okay, so we can keep down here. That means 2.46 moles. Okay, which would be B. Okay. Let's see. 34. 34. You're holding 4 balloons. Each contains 6 grams of a different gas. The balloon containing which gas is the largest? All right. You got 4 balloons. And let's say they get bigger from left to right. Each one has a different gas in it. We're given gases to select from. Nitrogen, helium, krypton, and neon. Nitrogen, helium, krypton, and neon. Those are our 4 gases. We need to put those in here. Let's try putting them in order. We got 6 grams each. What we want to know is, what's the order? Then we can pick out the one that's in the largest one. All right. So what makes one bigger than the other? The bigger one has more particles in it, has more molecules, more atoms. So how do you get more atoms when all the masses are the same? The one that's the largest is going to be the one that has the smallest mass for each atom, because it takes more of those small atoms to make 6 grams than it does for the bigger atoms. So, what's the molar mass of nitrogen? Well, it's about 28 grams per mole. Helium is 4. Krypton is about 36, about 84. And neon is 20. Okay. So the smallest one is going to be krypton, because it's the biggest atom. You have fewer of them required to make 6 grams. The biggest one is going to be the smallest one, helium. Right? So we've used that one and that one. So neon, nitrogen is going to be here, and neon is going to be here. Right? So the biggest one is going to be helium. Now, if I change the conditions on this question, say on the final exam, say, which one would be the smallest one? Right? Then you would be able to say, oh yeah, it's krypton. They're the same mass. It takes fewer krypton atoms to make 6 grams. So it's a smaller number of moles, which makes a smaller balloon. All right. Let's see what we got here with 38. Okay, zinc metal is added to a hydrochloric acid to generate hydrogen gas and is collected over a liquid whose vapor pressure is the same as that of the pure water at 20 degrees, which is 18 torr. Okay, zinc metal is added to hydrochloric acid plus HCl, and that yields plus hydrogen gas. Okay? So that would be 2 there. That would be our balanced equation. But we're collecting this gas over water. Yeah, well, it doesn't say it's water, but we're going to take it as pure water. All right, so we've got this reaction vessel here, right? Okay, and we've got a container. And we have graduated cylinder, marked off, right, with volumes. Okay. And initially it was filled to the top with this liquid. And as the gas was produced from this reaction over here of zinc plus hydrochloric acid, we get hydrogen gas going this way. We're collecting the hydrogen up here. Okay. All right. So, the volume of the mixture is 1.7 liters. So this is a big cylinder. 1.7 liter volume total. And the total pressure is 0.508 atmospheres. So the total pressure is 0.508 atmospheres. All right. That's kind of an odd problem. The total pressure is 0.508 atmospheres. Well, what's the pressure outside? Well, we're not told. We're just told the pressure inside. All right. So we're asked to determine the partial pressure of hydrogen gas in this mixture. So what is this total pressure equal to? It's actually equal to the pressure of the liquid here, whatever that liquid is, plus the pressure of the hydrogen. We need to find out what's the pressure of that liquid. Well, if it's at 20 degrees, and it says it's 18 torr. So this is 18 torr. We need to know what that is in torr. So what's 0.508 atmospheres in torr? 0.508 atmospheres. Convert to torr. How many torr in an atmosphere? 760 torr. So 760 times 0.508 is 386 torr. Okay, 386 torr. That means the pressure of hydrogen should be equal to 386 minus 18, or 368. Okay. That's how it works. Okay, scroll a little bit. 39. All right. Solid carbon dioxide is placed in a Ziploc bag. All right. Solid carbon dioxide sublimes, turns directly from solid to gas at a rate of 0.726 grams per minute. If the pressure builds to 3.75 atmospheres at a temperature of 21.1 degrees C, what's the final volume of the bag after 4.97 minutes? Excuse me. Let's assume that the solid carbon dioxide left in the bag is a negligible volume, so we can ignore it. All right, so what do we got to start with? We got the solid carbon dioxide going straight to gas. Okay? At what rate? 0.726 grams per minute. 0.726 grams per minute. So if we let it go for 4.97 minutes, how many grams is that? 4.97 minutes. And 0.726 grams per minute equals what? How many grams do we have? We have 3.608 grams. Okay? I'm going to keep an extra decimal to avoid rounding error. So that's how many grams of CO2 have been converted into gas. The pressure inside the bag is 3.75 atmospheres. So pressure equals 3.75 atmospheres. Okay. And the temperature is 21.1 degrees. 21.1 degrees C plus 273. I think we're going to need that anyway. All right, so that's 294K. What else do we know? That's it. The question is, let's see, what's the final volume of the bag? Okay, so volume is unknown. All right, if we want to know volume, and we know the temperature of the gas, and we know the pressure of the gas, we know the mass of the gas, and we know what gas it is, we can find out how many moles that is. This is where we're headed. Right? We know the pressure, we know the temperature, we know R is a constant. We need to find moles. Then we can solve for V. Right? So we need to convert carbon dioxide into moles. So how many grams is carbon dioxide? We need to know the molar mass of carbon dioxide. So one carbon is 12.01 grams per mole, and two oxygens, 16. Right? So that's 32. Let's see, 32 plus be 44.01. There we go. That's the molar mass of carbon dioxide. Divide that into 3.608. 44.01, we get 8.199 times 10 to the minus 2 moles. Now we can substitute values in here. Right? 8.199 times 10 to the minus 2 moles. R is 0.08206 liter atmospheres per mole K. Temperature is 294.1 and divided by pressure, which is 3.75 atmosphere. So this is going to be the volume of the bag in liters. So 0.528 liters. How about your answers? Your answers are in milliliters. So how do you get milliliters out of that? Well, remember, if we're going to make the unit smaller, the number has to get bigger. Right? So if we make the unit milliliters, how much smaller is milliliters than liters? It's 1,000 times. So that means 3 decimal point movements. 1, 2, 3. So that's 528 milliliters. And there it is, B. All right. Takes care of 39. Let's see what's next. 41. How we're doing on time? Okay. We're in good shape. You're holding 2 balloons of the same volume. There. We got a balloon here with that volume, and we got a balloon here with exactly the same volume. Okay. So, are they identified? One balloon contains helium, the other balloon contains neon. So this one has helium in it, and this one has neon in it. This is the volume of helium equals the volume of neon. Okay. 1.05 grams of helium. All right, we're given that. The other balloon contains neon. What's the mass of the neon in the balloon? Well, the volumes are the same, and we have to assume that the pressures are the same also. Right? The pressure on the helium balloon is atmospheric, whatever that happens to be. So that's the same. And we also have to assume that the temperature is the same. Right? So, what did Avogadro say? He said, if the temperatures are equal, the pressures are equal, the volumes are equal, the number of moles are equal. So the moles of helium equals the moles of neon. Okay? All right. So let's introduce one other factor in here. We're looking for the number of grams in the neon blue. With all these things equal, the only difference between the helium and the neon is the individual mass of each of the atoms. What's the ratio here? Helium is about 4, right? Yeah. Neon is about 20. So the ratio of the masses of the atoms is 5 to 1. This neon is 5 times as heavy as that one. If you've got exactly the same amount of moles of each in those two balloons, then this one should be 5 times as heavy as that one, because each of the atoms is 5 times as heavy. So 1.05 times 5. 5.25 grams should be our answer. The closest we come to that is 5.29. Okay, here's why. This is 4.00. This one is actually 20.18. 20.18 divided by 4.00. So what's that value? And I got these values off the periodic table, by the way. This is 5.045, and that's times 1.05. How about that one? 1.05. Excuse me. 1.05 enter 5.045. This is 5.30 actually. 30. So either way, the best answer here, and that's what I always say, multiple choice questions. If you have unique answers for all the selections, then choose the best one. And the best one here is A, 5.29. We did a little bit of estimating, and that threw our answer off by a small amount. All right, who's next? 44. A gas occupies 42.6 liters at 2 atmospheres and 27 degrees. Calculate its volume if the pressure is decreased to 1 atmosphere at constant temperature. All right, so we're given, this looks like a before and after situation. So before, we have 42.6 liters. So the volume 1 is 42.6 liters. The pressure 1 is 2 atmospheres. And the temperature is 27 degrees. All right. How about calculate the volume? Okay. That's the unknown. We want to calculate the volume after. If the pressure is decreased to 1 atmosphere, so the pressure after is 1 atmosphere. What about the temperature? Temperature stayed the same. So temperature 2 is 27 degrees. See, right? So the temperature didn't change. We can look at this several ways. We can try to figure out which law references it, or we can use the combined gas law, right? P1 V1 over N1 T1 equals P2 V2 over N2 T2. And then we can say temperature didn't change, right? So we don't need the temperature term. Number of moles didn't change, right? Because this is not a chemical reaction and we didn't add any gas or subtract any gas. Okay. So that goes out. So we're actually looking at P1V1 equals P2V2, and that's Boyle's law. So we're going to solve for V2. P1V1 over P2. Okay. So P1 is 2 atmospheres. Volume 1 is 42.6 liters, atmospheres. And the final pressure is 1 atmosphere. Right. So 2 times 42.6 is 85.2 liters. Right. So B is the answer. Right. We could have reasoned it out and figured, okay, this looks like Boyle's law. But for me, it's simpler to use the combined gas law and then say, all right, what's constant? Just eliminate those terms. And what are you left with? Now I know we're left with Boyle's law. Okay, 45. You have partially filled party balloon with 2 grams of helium gas. You then add 3 grams of hydrogen gas. So we got a balloon. Start off with 2 grams of helium. And then we add what? 3 grams of hydrogen. Oops, not water. Hydrogen, there we go. And that gives us a balloon now that's probably bigger. And now we have 2 grams of helium and 3 grams of hydrogen. Okay. Assume constant temperature and pressure. Temperature and pressure didn't change. How many times bigger is the party balloon? Comparing before and after the hydrogen gas has been added. Choose the best formula to use this to solve this problem. Okay. All right. All right. So, this is an expression of Avogadro's law. If you have a volume here, a volume 1, and this is a volume 2, then volume 2 is going to be bigger than volume 1. But the ratio of volume 1 is not to grams. The ratio is to moles. Right? So as we increase the number of moles, we get an increase in volume. So if we go from N1 to N2, V1 increases to V2. Okay. Now we could look at this from the mass standpoint and say, all right, if I convert that to moles, and then I convert this, but we're still coming back to Avogadro's law. Even if you convert these to moles and moles and moles and say, what are the absolute values? You're still going to come back to this rule, right? So let's see, are there any in there? Temperature's constant, temperature's constant, so it's not going to matter. Pressure's constant, so it's not going to matter. P2 over P1 is going to be 1, right? That doesn't help us at all. How about V2 and V1? Well, for C, the ratio of volume to volume is not proportional to mass at all. It's proportional to moles. So D is a better choice. And E, since pressure is constant, then Boyle's law doesn't make a difference. We're looking at Avogadro. And if we solve it for V2 over V1, right, we move this V1 over here, right? Then move this N2 over there. And that should be D, right? Ultimately, that's the equation that solves our problem. All right, 46. Still working with gas laws, looks like. A gas occupies 18.5 liters at standard temperature and pressure. What volume will it occupy at 735 torr and 57 degrees? All right. So if it's 18.5 liters, that's volume, 18.5 liters at standard temperature and pressure. What are those values? Standard temperature for a gas is 0 degrees. Right, so that's 273 K. Standard pressure is 1 atmosphere. Right? The question is, what will be the volume with these new factors? We don't know that. But the temperature has changed to 57. Okay? So that's 0 and 13, 330 K. And pressure. Pressure has changed to what? 735 torr. Well, we need atmospheres. 735 torr divided by 760 equals what? How many atmospheres? Actually, the pressure is decreasing from 1 atmosphere. 967. Okay. So how do we solve this one? Well, P1 V1 over T1 equals P2 V2 over T2. And I use the combined gas law, and since the number of moles didn't change, I just left the moles out. Now we want to solve for V2. V2 equals P1 V1 T2, right? That comes over here. This one goes over here. Over P2 T1. Now we just plug in the numbers. Once you've got the values in your table, then you can put them in the right place in the formula. If you don't put them in a table first, then you run the risk of inserting these values in the wrong places here. So pressure 1 is 1 atmosphere. Volume 1 is 18.5 liters. Temperature 2 is 330 K. Pressure 2 is 0.967 atmospheres. And temperature 1 is 273. Okay. So that's the thinking part. The rest is just number crunching. 0.967 and 273. So I get 23.1 volume. 23.1 liters. Okay, that should be A. All right, scroll. Let's see how we're doing. We're doing pretty good, actually. How about 48? Oh, acids and bases. Okay. Identify the Bronsted acids and bases in the following. A stands for acid, B stands for base. All right. HSO3 minus, HSO3 minus plus CN minus yields HCN plus SO3 2 minus. Okay. What's a Bronsted acid? Bronsted acid is a proton donor. So which one donated a proton? Well, it looks like this one, SO3, lost that proton and ended up SO3 2 minus. So this is our acid. It donated a proton. Which makes what? It makes this one the conjugate base. That means this is the acceptor, and it makes that a conjugate acid. So ABAB should be the correct one. That's B. Right there. 49. Which has the higher hydrogen ion concentration, 0.4 molar rubidium hydroxide or 0.2 molar calcium hydroxide, which has the higher hydrogen ion concentration. Okay. So let's look at what happens when you put these in water. 0.4 molar rubidium hydroxide. 0.4 molar rubidium hydroxide. And 0.2 molar, 0.2 molar calcium hydroxide. All right, what does this one do? When it goes into water, it makes rubidium plus hydroxide. Okay, and this one makes calcium plus 2 hydroxides. Okay, so what's the concentration of hydroxyls here? If this concentration is 0.4, this one is also going to be 0.4 molar. If this one is 0.2 molar, and it makes 2 for every one, this one is also going to be 0.4 molar. They're exactly the same hydroxide ion concentration. What does that mean? That means when they go into solution, the reaction they produce with water is going to generate the same hydrogen ion concentration. So neither is higher, right? They're both the same. Hydrogen ion concentration will be equal. Now it's going to be basic. Hydrogen ion concentration is going to be low, but it is going to be equal. Exactly the same. Number 50. All right. Number 50. Calculate the pH of an acid solution containing 0.044 molar HNO3. 0.044 molar HNO3. What do we know about this solution? What we know about this solution is that it's composed of a strong acid. So that means if this is 0.044 molar in that compound, it's also 0.044 molar in hydrogen ions. So in order to calculate the pH, we just need the negative log of 0.044 molar. Which would be 1.36 pH. Okay. Remember, when we take the log of this number, it has two significant figures. That means the pH is going to have two decimal places. Right? So the number of significant figures relates to the number of decimal places. That's just a fact of logarithms. All right. That was 50. 51. Which of the following statements are correct? Let's see. A through E. A, B, C, D, and E. Let's see, D and E are oddballs. All of the above are correct. All correct. And E, none are correct. Okay. Okay, so let's look at A, B, and C. In a neutral solution, the concentration of hydrogen ions equals the concentration of hydroxyl ions. That is true. That is a definition of neutrality. In an acidic solution, hydrogen ions exceed the concentration of hydroxyls. That is also true. C, in a basic solution, the hydroxyl ion concentration is greater than the hydrogen ion concentration. That is also true. So all are correct. D is the answer. How about 52? Calculate hydrogen ion concentration in a solution that's pH 5.15. All right, pH equals 5.15, which by definition is the negative log of hydrogen ion concentration. Okay, so we need to solve for this one. How do you do that with logarithms? Well, this is base 10. Okay? And the definition of logarithms is this value is equal to the power of 10, with that being the power. But we got a negative here, so we have to move the negative first. So negative 5.15 equals the log of hydrogen ion concentration. So with that 10, that means 10 to this power equals hydrogen ion concentration. That's the definition of logarithms. Yeah. So how do you do that in your calculator? Well, most calculators have a LOG key. And then there's a shift function above the LOG key, 10 to the X. So you take the minus 5.15 power of 10. 5.15, and I change my sign. Then I go to the 10 to the X. And I get 7.08. Actually, there are two decimals, so I have two significant figures. 7.1 times 10 to the minus 6 molar. There you go. Okay, 53. A solution where hydrogen ion concentration is 10 to the minus 13th molar is acidic, neutral, basic, or strongly acidic. Okay, let's look at that. Equals 10 to the minus 13. Okay. Remember your scale, your pH scale. Neutral pH is 7. Strongly basic would be in the neighborhood of 14. And strongly acidic would be in the neighborhood of 1. So what's this one going to be? Negative log of that value yields 13. 13 pH is out here. It's strongly basic, right? It's basic. Let's see. Yeah, D, that's right, basic. That's our only choice. Right? D is basic. All right. Who's next? 58. See how we're doing on time. Got 20 minutes left. No, I didn't pull out. Oh, just a second. $58. Okay. Yeah, I think we're not gonna make it to the end today. So when I've run out of time, I'll stop and we'll pick it up on Thursday. Choose the pair of compounds with the same empirical formula. What's the empirical formula? The empirical formula is the simplest whole number mole ratios of elements in a compound. So for instance, the example I give you in class is CH, C2H2, C6H6. Those are all the same ratio, 1 to 1, 2 to 2, 6 to 6. So for this one, this would be CH, and each one of these would have to be multiplied by 6. This would be CH, each one multiplied by 2. This would be CH, each one multiplied by 1. That's your factor. That's your multiplier. So if we want to find a pair that have the same empirical formula, they would vary by only that factor. Okay. How about A? H2O and H2O2. No. 2 hydrogens and 1 oxygen. And hydrogen peroxide has 2 hydrogens and 2 oxygens. That won't work. How about B? There's B. C2H2 and C6H6. So we found our answer actually, but you can look at the others and see that you cannot multiply one by a factor, or you cannot find a simple formula multiplied by a factor that gives you both of the compounds. So the answer is B. How about 60? Acetylene gas is 92.3% carbon and 7.7% hydrogen. Its molar mass is 26 grams. What's its molecular formula? Okay, remember when this is a two-step process. Percent by mass can be used to give you the empirical formula. Easy. Then you need the actual molar mass of the compound to go from empirical to molar mass. So we do the empirical first. 92.3% carbon. So carbon is 92.3% by mass, and hydrogen by mass is 7.7%. Remember, the compound formulas are ratios of atoms and moles of atoms. Numbers, not masses. These ratios are not correct. We need to convert carbon and hydrogen into moles so that we can ratio them. But percent is a dimensionless number. We do know, however, that it's by mass. So this is grams per 100 grams of compound. So if we assume 100 gram sample, now that means we have 92.3 grams of carbon and 7.7 grams of hydrogen. Now we can convert to moles. Okay, hydrogen is 1.01 grams per mole. Carbon is 12.01 grams per mole. All right, so 92.3 divided by 12.01 is 7.69. Okay, that's moles. And 7.7 divided by 1.01 is 7.6. 7.62. All right. Those are so close. Normally what you do is you take the smallest one and divide through by it. This is exactly one, and this is so close to one that you might as well. So our empirical formula is actually 1 carbon and 1 hydrogen. Now what we need is that multiplier. And that's where the molar mass comes in. We ratio the mass of this unit right here, which is 12.01 plus 1.01 is 13.02 grams per mole of that unit. I call that the empirical weight. The molecular weight, or the molar mass, is 26. So if we take the molar mass and ratio it to the empirical mass, then we get 26 divided by 13.02, which is very close to 2. That means this is 2, and the formula is C2H2. Okay? All right. I'll tell you what, before we get too far, this is part 1. Part 2 will be on Thursday. So let's see, maybe we can get 61 before I have to stop. 61. You have 1 mole of each compound below. Which has the greatest mass? Okay. If you have 1 mole of each one, then all we have to do is compare the molar mass of each one, because molar mass is grams per mole. So what's the molar mass of each one of these guys? A, B, C, D, E. All right. In this case, you have to be able to write the compound from the name. Okay. Sodium hydroxide, sodium hydroxide, barium carbonate, barium carbonate. Carbonate is a polyatomic ion with a 2- charge. Barium is an alkaline earth with a 2+ charge. So you just need one of each. That's all there is. Okay? That one's written correctly. How about C? Iron 3 sulfate. So iron 3, like that, and sulfate is a polyatomic like that. So that means take this 2 over here, take that 3 over there, and now we have balanced charge. Okay? D, ammonium nitrate. Ammonium and nitrate. That's it, one of each. Lead 4 oxide. Lead 4+, and oxide 2-. So we need 2 oxygens to balance the charge. Okay, now that you have the formulas, we can calculate the molar mass. Right? Sodium is 23. Right? So this is 23 plus 16 for oxygen plus 1.01 for hydrogen. Which is 40.01 grams per mole. Barium is a big, big atom. 137.33. 137.33. Carbon is 12.01. And oxygen would be 3 times 16. Okay? So 48 plus 12.01 plus 137.33 is 197.34. There we go. Iron. 2 irons. 5585. Okay. Plus 3 sulfurs. Sulfur is 3207. And then 12 oxygen. Okay. All times and then 32.7, 55. This is 399.91. Yep. Ammonium hydroxide. We got 2 nitrogens at 14.01 each. We have 4 hydrogens. And we have 3 oxygens. It's 80.06. Okay, and the last one, lead. Lead is 207.21. There's only one of them. And then 2 oxygens. 32 enter in 207.21. 239.21 grams per mole. So which one weighs the most per mole? Well, it looks to me like this one. Iron 3 sulfate. All right. That was simple enough. As long as you know how to write the compounds, you're in good shape. Right. Got time for at least one more. A certain compound has an empirical formula of NH2O. NH2O. And I assume we're going to have to multiply by some factor. Its molar mass is between 55 and 65. So molecular weight is 55 to 65 grams per mole. All right, how do we compare? We need the empirical weight for this one. So nitrogen is 14.01. 2 hydrogens is 2.02. And 1 oxygen is 16. Right? So we have 3, 0, 8, 12, 32.03. Right? So if x equals 1, 32.03 is not equal to 55 to 65. If x equals 2, 64.06 is equal to, right, between those two. So x equals 2. That means N2H4O2 is the formula. N2H2O2. Oh, excuse me. N2H4O2, B. Oh, I got time for one more. 64. What's the molar mass of Li2SO4? Lithium sulfate. Well, let's see. Lithium is 6.94. 6.94 times 2 plus sulfate is 3207. And then 4 oxygens. All right, so what is that? 6.94 and 2 times, and then 32.07, and then 64. 109.95 grams per mole. The best answer is B, 109.88. Right. So that was 64. This might be a good place to stop. And we'll pick it up with 71. And make a note. 71. Here we go. So that's going to be on May 2nd. Okay. All right, we'll pick this up again on Thursday.